right, and welcome to our video about the seasons. Since the dawn of time, humans have wondered why we have shorter, darker days in the winter and days more full of sunshine in the summer, why it gets warmer and colder as those seasons pass. So naturally, people have tried to come up with solutions for why it's happening. And one reason many people think is because the Earth must be closer to the sun in the summer. That makes sense. If the planet is closer, we'd be warmer. But in fact, that's not what we see here in the northern hemisphere. Take a look at this image. And on the left, we have the planet in January at 147 million kilometers from the sun. So on the other side, July, it must be summer, it must be even closer, less than 147 million kilometers. But it's actually 5 million kilometers more. It's 152 million kilometers away in July. The Earth is farther away from the sun in the summer in the northern hemisphere. So it has to be something else. So some of you are probably thinking, wait, I've heard that the Earth spins on an axis that's tilted. And in fact, that is true. Most globes you see in classrooms or stores look like this, with the North Pole and the South Pole not quite at the top at the bottom, but a little bit off. In this image, you see what we call the axis, which is an imaginary line going from the North Pole to the South Pole through the Earth and up and down and away from the Earth in an infinite line. It's not a real thing, but it does serve to give us something to focus on and understand better what's going on. The Earth is somewhat tilted, and that means when the globe spins around, when the Earth spins around, it's not the case that the equator and the area towards the middle, the belly of the Earth, is always closest to the sun. So as we move through the seasons, as you can see in this image, this axis is always oriented or pointing in the same direction. In this case, it's higher on the right and lower on the left, whether it's summer, winter, spring, or fall. And there's something else we need to consider, which is if it was just about the distance from the sun, that would mean that everybody on Earth, North America, South America, Asia, and Africa, would experience cold winter at the same time. But that's not how it works. In the northern hemisphere, where we live closer to the North Pole, we have winter, while at the same time in South America and Africa in the southern hemisphere at the bottom of the Earth, that's when they have their summer. If it was about being closer, further away from the sun, then we should all have winter at the same time and we should all have summer at the same time, but that's just not how it works. So this challenges the idea that it's about being closer and further away from the sun. This is evidence against that claim. So the next question you're probably asking then is, well, what difference does the tilt really make? And so some people will say, oh, I get it. The part of the Earth that's closer to the sun is going to get warmer because it's closer. If you look at this image of the globe, you'd say, well, the equator is a little bit closer to the sun, right? The sun might be on the right, all the way over on the right, millions of miles away. And up there at the Arctic Circle, they're just further away from the sun. Now, this makes sense, but it's not really what's happening. So let's look at this model. That's Bohannon Middle School at the bottom, and that straight line is a kilometer long and will end up at Round Table and the library and the fire station. So it's a kilometer away. And Bohannon will be the sun, and that would be 9 meters tall, not quite as big as the gym. And down Hesperian at Round Table, we'd have the Earth at about the size of a golf ball to scale. So, if you were floating above the library and the sun was burning at Bohannon, would you feel a difference in heat if you put your arm out in front of you compared to your face, or one arm a little further than the other? In fact, only 8 centimeters further. Um, at that distance, I would claim you would not feel the difference. And that gets back to this picture. It would not be warmer at the equator than the Arctic Circle just because it's a little bit closer. It doesn't work out that way. So we have to look for something else. So we're going to look at the classroom model that we usually use in our labs. And here we have a globe with a tilted axis set up against a wall. We're going to move it from that position and fall to winter, which would be here relative to our flash or our light bulb, which is our sun, and then spring against this wall, and that takes us to summer, where we round out the four seasons with the sun in the center. The earth is on a tilt, you'll notice, and so in every position it's going to be tilted towards the same wall, towards the same side of the house. And now lights off, and we're going to take a look at our globe in the fall, around September, and this time of the year is called the equinox. You notice the Earth is riding right as we look straight down. It's 50-50 lit up, and the North Pole is right on that line. So days at the North Pole here would have long shadows. The sun would be low. And now you'll see this little marker is set where the Bay Area is, right there. We're looking at it upside down. So as we spin the globe around, how much time would San Francisco have in night on this side, at the bottom of the screen, and then in day if it went all the way across at the top? The fact is there's 12 hours of daylight up here on the bright side and 12 hours of nighttime on the other. Things are equal. They're about the same. Equinox. And what if we look at it from the side view? We have that little tag, that little white tag where San Francisco is. And if we stop it right here, take a look at that angle. It's not really pointing at the sun. It's pointed up and to the right. So keep that in mind when we look at this globe in other positions in the room. And that's about, guessing, about 45 degrees for that tilt. And lastly, we're going to look at the Earth as it would appear from the sun. So we're just looking at the sunny side. And you saw San Francisco there. And I paused it here so that you can take note. You'll see that glare in the middle of the Pacific Ocean. So that'd be kind of the center, the place where the sunlight is most intense. And San Francisco's kind of halfway between the top there and that the equator, a little more towards the top, I would say. So just remember that positioning as we move ahead. Okay, so now let's take a look at winter in the northern hemisphere using our model. So it is winter, it is December, and we call this the solstice, the winter solstice. And we're starting off with our view from the sun, but what we really want to do is take a look at the North Pole. What is going on there? Let's start with that like we started with the last position. So actually we can't see the North Pole. It is in the dark. It's right there, but it is on the dark side of the Earth. So in the winter, day after day after day after day, there is no sunlight. It is nighttime. It is dark all the time. And there's San Francisco. Let's take another look at San Francisco then. We're bringing the camera up above the North Pole, and we want to see how much light San Francisco can get in a day as it goes around. It's in some of the light, but you'll notice it's not in direct light. It's an indirect light. It is not getting, well, you'll notice the shadows are long, so which means the light is not overhead, but at an angle, an oblique angle, or an indirect angle. And in fact, in the winter, we only get 9.5 hours of daylight, starting here in the morning. There's lunchtime and dinner time, and it's dark a lot. You know it in December. You feel it. You know when you're playing sports, it starts getting darker earlier. And the rest of the time it's in darkness at night. So that would be around about 15 hours of darkness in the day. Well, not as much bright, a lot more dark. Could that have an effect on the seasons or the temperature of the Earth? And now let's look at our side view. And that at the top of the screen is a marker for San Francisco. And you can see that it is, as it would spin around up there, it's getting those reduced daylight hours, just 9 hours, 9.5 hours of light. It's almost against the terminator where the dark side meets the light side on the globe. And so this is winter, very little light and not very direct light. And so let's finish this section by looking at the Earth from the sun. And here we see that marker for San Francisco practically at the top of the globe, practically in that all dark region, not getting direct light like it would if it was lower down, pointed right at the camera. Only 9.5 hours of light, most of the day spent in dark. So now let's look at March, at spring. We have the spring equinox. And we'll bring our camera, we'll look down from the top at the North Pole. And so if you were living here, the sun would never be going down very much in the sky or up very much in the sky. The sky would always have some color in it. And this is very different from our last season in winter where there was no light on the North Pole at all. Now let's talk about how many hours of light San Francisco would get in a 24-hour day. Well, half the globe is lit up, directed towards the light bulb, and the bottom half is the dark, and it's really 50-50. So if there's 24 hours in a day, San Francisco up here would be in sunlight for 12 of those hours. 12 hours in daylight and finishing up at night with an also equal amount of light. 12 hours of daylight, 12 hours of night in March. And now our side view to see the angle of San Francisco compared to the sun. And there's the Bay Area. And as you can see, it is leaning up about 45 degrees, similar to the fall. And so we'll finish this section with our view from the sun, and we can see San Francisco kind of turning and stopping here for a second. Now remember, last time in the winter, this was pointed much higher. It was much closer to the top of the globe or to the North Pole. Here it's coming back down. It's getting closer to pointing toward the sun. And now let's shift to summer, and San Francisco is here. We'll move it up to the top, and notice how much light is on the globe now. Notice this is the brightest we have seen it from the top. And if we drill down now towards the North Pole, what would it be like there day after day as the Earth spins? Well, it would be daytime 24 hours a day. The sun would get a little higher and lower in the sky, but it would not drop below the horizon. It would never be totally dark or really very dark at all. Next, let's use our model to see how much daylight San Francisco would get when it goes around one time. And from where we started, it's kind of hard to see. Even there, it's still in light, and it's more than 50% of the time. So morning time starts. This is more hours of daylight, and more light means more heat. In this case, in this model, that would be about 14 and a half hours of daylight and about 9.5 hours on this dark side. It's a lot more hours of daylight. And remember, it's summertime. Let's take a look at the direction or angle that light is coming from. Let's start by lining up San Francisco so it's pointing directly to the sun. We're looking from a side view. And here you can see that San Francisco is pointing more closely to the sun, at least. Where before it was up at a 45-degree angle and a 60-degree angle. Here it looks like only about a 10 or 15-degree angle away from a direct line between the Earth and the sun. Okay, laser thermometer and a globe. I'm going to put the globe on that stand behind me and let it be in the sun for a few minutes. Then I'm going to measure the temperature from the side of the globe that's pointed closer to the sun, and then from the edges to see if there's a difference. So Africa seems to be the place where I'll take my central measure. This globe has been out now for about 3 minutes. So I'm going to take temperatures from the point closest to the sun, or most directly, I shouldn't say closest, most directly to the sun, and the areas where the sunlight is not hitting at a direct angle. This is direct, but here the light is coming down at what we might call in math an oblique angle. So, shadow side, 75 degrees Celsius. Here, 77 degrees Celsius. Here, 82 degrees Celsius. Here, 90 degrees Celsius. Here, 95.3 degrees Celsius. Now, remember, the globe is spinning all the time, so any land in this area would be getting hottest throughout the day.